All right, let's jump into derivatives. So the limit is the foundation for all calculus. There's two parts to calculus, and the first part is derivatives, second part is limits. First part is derivatives, second part is integrals. Limits are the foundation. So if you didn't feel pretty confident with those two important things that I mentioned in the video from the bookwork that was assigned Monday due Tuesday, today, go back and rewatch that because it's really important. Now this is how we're applying limits to derivatives to build a foundation for derivatives, okay? So pause me for a second and write all this down and then I'll start explaining. All right. So the derivatives are all based on the tangent line. We all know what tangent means, right? So tangent line, there are so many physical applications of the tangent line. I'm not going to be able to teach them to you. You'll learn them next year. But it's actually kind of neat if you're kind of nerdy like me. So we want to know we're going to start with the slope of the tangent line. We'll worry about the equation. The equation's super easy. It's just an algebra 1 thing. We want to know the slope of the tangent line. Well, all we know is this point right here, 1, 1. Oops, sorry. That's this guy right here. Okay. 1, 1 is a stationary point. It's not moving. It's the point, the only point that is on both the line and the curve. Okay. What we're going to do is we're going to talk about secant lines. Secants cross at 2 or more places. Now, this is going to get messy. I probably should have told you this before. If you didn't draw your graph nice and large like I did with the 1 unit being pretty big, you're probably going to want to pause and redraw because this is going to start getting kind of messy. If I find the slope of this line, 0, 0, and 1, 1, let's start out with that, okay? So this is, oh, darn it, I'm trying to color code this here. This point is always going to be the same. I'll fill more in later. I can find the slope between these 2 points pretty easily, right? I'm going to go y minus y over x minus x, and I'm going to get 1. The slope of that line probably isn't very close to the slope of the tangent line, okay? So I'm going to work my x value closer to the x value at the point of tangency. Point of tangency is at x equals 1. So I'm going to, instead of having x equals 0, I'm going to go to x equals 0.5, something like that. The slope of that line is definitely closer to the slope of the tangent line than this first one was. These are all secants. The greens are all secants. They cross the curve at 2 or more places. Tangent is only 1. So I'm going to use 0.5 as my x value, which means my y value is 0.5 cubed, right? If x is 0.5, then y is 0.5 cubed. I don't even need to figure that out because I'm going to use my calculator at this point. I'm going to find the slope of this line using this point and this point, okay? This is not a huge thing on the calculator, so I'm recommending in the assignment that you watch this one time through to understand the concept, and then you go back and rewatch so you can just do the steps on the calculator without having to memorize them. There's no reason to memorize these steps on the calculator. So I'm going to go stat, and then I'm going to hit enter to edit. I'm going to put in all of these x values. How do I want to do this? I'm going to put in all of these x values. So what's going to happen is I'm going to get my x value closer and closer to this x value, starting at 0 and then going to 0.5. And I could go like 0.7 and 0.8. But the idea of a limit is to get really stinking close. Okay. So I'm going to go 0.9 and then 0.99. And if I could draw in those secant lines, which I can't, the picture is too small. If I could draw in those secant lines, you would see that the slope of the green is getting closer and closer to the slope of the tangent line until we actually get a value. So let me show you how it shows up, not visually because that's too hard to do, but on the graph numerically. And then, I bet there's something we could do on Desmos so I could show it to you visually. All right. So I'm going to type in these x values, 0, 0.5, 0.9, 0.99, 0.999. And I honestly don't know how far I need to go, so I would rather go further than I need. than to not go far enough. Because once I start typing into these other columns, excuse me, I can't add anything here later. Okay. Now, what do we know about limits? What has to happen for a limit to exist? Pause me and think about that. Okay, so hopefully you said to yourself, the the left-hand limit has to be the same as the right-hand limit. So I need to approach one not just from the left side, but I also need to approach from the right side. So I could do like 2 comma 8. That's really far away though, right? 2 comma 8. I want to get really close. So really stinking close is what I always say when I'm teaching calculus. Limits aren't about just being kind of close. They're about being really stinking close. Oh, I didn't put in, darn it. I didn't put in that one. So I've got 1, 2, 3, 4, 1, 2, 3, 4. I should be good there. Okay. And again, I don't need to calculate the y values because my calculator is going to do that for me. So I'm going to put in the 2 and the 1.1 and the 1.01 and the 1.00, whoops, 1 and the 1.0001. Okay. Now I'm going to use the calculator to calculate all of these things for me. Could I very easily cube all of these x values? Yes, absolutely. I totally could cube all